So we're Team NeMo-Ray, the winners of the NVIDIA Hack for Impact Hackathon. We built NeMo-Ray to develop the future of London's infrastructure and 4G networks.
Emergency services can't afford to fail. Our current system is not fail-proof. Because of this, the UK government has pledged to create the ESN, or the Emergency Services Network, and we built the platform to accommodate this initiative.
Emergency services calls ride on an unreliable commercial mobile network, one that was never built to be failure-proof. A single down mast can black out coverage exactly where it's needed most. Britain is upgrading the emergency service network by 2030. Thousands of frontline responders all to run on another 4G network. We need to make sure this is dependable.
The UK Space Agency is already running a funded procurement to 2030 asking how satellites can plug the gaps. The problem is real, the money's there, and nobody has solved it.
We built a 3D digital twin of London's network by combining cell tower locations with UK building geometry to ray trace coverage maps. Using our Nematron agent, we can simulate failure events from the network in real time and work out the best way to restore coverage. We identify exactly which area has gone dark and calculate optimal places to deploy satellite-equipped cell on wheels. These units determine which satellites are overhead at real time and routes to them, keeping emergency services connected when the ground network can't.
So we're building a 3D digital twin using Nematron 3 Super, Siona RT, and Co-opt.
We used NVIDIA Siona RT for tracing 4G rays across London, NVIDIA Co-opt to optimize where cell on wheels should be deployed to reduce coverage gaps, and NVIDIA's Nematron Super reasoning model to orchestrate deployment and simulation.
Siona RT is at the core of our project. We used it to create an accurate network coverage map of London based on existing mast locations and 3D building data. We then used those insights to propose ways to optimize the network to ensure our emergency services always stay connected.
Here is an accurate coverage map of the existing network. Every map you see is real physics, not a guess. We pull London straight from OpenStreetMap, build every building in 3D, and drop in the real phone masts as a true digital copy of the city. Then NVIDIA Siona traces the signal from each mast as it bounces off buildings and fades out, like light in a game. That's how we know exactly where coverage holds and where it drops. All of this runs on the DGX Spark locally, fast enough to be live. A full London solve takes seconds, not hours. So when a mast goes down, we can retrace just that area instantly and show the new dead zones on the spot.
A digital twin can show you where the network breaks, but it can't reason about it. That's where Nematron comes in. It's our brain sitting on top of the digital twin running locally on the DGX Spark. We run Nematron locally using NVFP4 on VLLM as a tool calling React agent. The operator just talks to it. It reasons, decides which tool to call, reads the result, and reasons again. It drives 12 real tools. Examples include run Siona coverage, run Co-opt to place masts, simulate a mast outage, deploy a cell on wheels, check a Starlink backhaul, etc. To act on the real world, however, we gave Nematron a spatial knowledge graph of London. When the operator says the nearest fire station to the Shard, Nematron turns the name into coordinates, finds neighbors, and moves the map camera there. NeMo-Ray is built entirely on real-world open data. We use Ofcom's SiteFinder Mast Register, which lists every EE4G site across Greater London, combined with OpenStreetMap's 3D building footprints, which Siona ray traces against. We layer on real locations of the London Fire Brigade, police, and NHS hospitals to ground every outage in the emergency services it actually affects. And finally, we also pull live Starlink satellite orbits to validate backhaul.
When a cell tower goes down during a major incident, you need to know instantly whether Starlink can fill the gap and exactly which satellite to point at. Our system pulls live 2-line element orbital data from Sealy's track, propagates every Starlink satellite's position in real time using SGP for orbital mechanics, and for any location in London tells you which satellite is overhead, the elevation angle for the dish, and an estimated round-trip latency.
And for the future, we're looking forward to delving further into this project with a more robust dataset and digital twins so we can make an accurate representation of the upcoming ESN that the government is about to deploy.